In today's lecture, we will look at the concept of the principle of superposition of electric fields using the electric dipole. Let's first define what an electric dipole is. The definition is the configuration of two equal and opposite charges separated by a distance is called an electric dipole. It is convenient to define a quantity called the electric dipole moment given by the symbol P, and the electric dipole moment is given by Q times D. It turns out that P behaves like a vector having a magnitude Q times D and a direction pointing from the negative charge to the positive charge along the line joining the two charges. It is beneficial here to draw a figure. If this is minus Q and this is plus Q, then this configuration of charges forms an electric dipole. And the electric dipole moment vector is given by this arrow. The line joining these two charges is sometimes called the axis of the dipole. To illustrate the concept of the principle of superposition of electric fields, we will calculate the electric field that the dipole produces at any point P along the perpendicular bisector of the dipole. We are interested now in calculating what is the electric field at point P. As you can notice, since this is a bisector, this is d by 2 and this is d by 2. Sometimes in other textbooks, you may notice that the distance between the two charges minus Q and plus Q is given by 2d. That is just for the sake of convenience, nothing more than that. So now let's see how the principle of superposition can be applied. If we complete this right angle triangle, you will notice that the electric field due to plus Q at P will be this particular arrow, and the electric field due to the minus Q charge will be in this direction. So this will be E minus. The reason for these arrows is, as stated in lecture 1 of this chapter, is because you have to imagine at P a test charge is placed and the minus Q will attract the test charge and the plus Q will repel the test charge. Let us calculate E plus and E minus, the magnitude. E plus equal to E minus is equal to 1 by 4 pi epsilon naught Q divided by R square. But you will notice from this right angle triangle that R square equal to x square plus d by 2 whole square. So the net electric field at any point P, or the net electric field at this point along the perpendicular bisector, is given by E of P equal to E plus vector plus E minus vector. Now this vector addition can be simplified further. How do we do that? Let us resolve E plus into two components. One is the horizontal component. Let us call it E plus along x direction, and then another one along y direction. So let's call it E plus y. Similarly, we can resolve the E minus vector into horizontal and vertical components. So this will be E minus along the x direction, and this will be E plus along the y direction. Rather, sorry, this will be E minus along the y direction. Let me erase this and rewrite it. E minus y. You will notice that E plus x and E minus x are equal and opposite vectors. So therefore, they will not contribute to this vector sum. And only these vectors will contribute and they will add up. So let us see what is E plus y and E minus y. Once again, from the symmetry of the right angle triangle, it should be clear that the magnitude E minus y will be equal to E plus y. So let's find out what is E plus y. If this angle is theta, then from the right angle triangle here, you can notice that this angle is also theta, because this line is parallel to this line, and this whole thing can be treated as a transversal. So this equal to this from the property of parallel lines. So let's write what is sine theta and cos theta. So here sine theta will be given by x by r, and cos theta will be given by t by 2 divided by r. From the triangle, it is clear that since only the vertical component contributes, E plus y will be given by E plus y is equal to E plus cos theta. Therefore, let us substitute E plus y and E minus y into this equation. If we substitute E plus y and E minus y into the above equation, we get E plus or E of P equal to E plus cos theta plus E minus cos theta. Since E plus and E minus have the same magnitude, we can write this equation as 2E plus cos theta. Let us substitute cos theta and E plus and E minus from this equation. Therefore, E of P equal to 2 E plus, which is 1 by 4 pi epsilon 0, Q divided by R square. Cos theta equal to D by 2 into 1 over R. So let's simplify this expression. This can be written as 1 by 4 pi epsilon 0 Q divided by R cube. But we already know what is R squared. So finally, the electric field at point P along the perpendicular bisector of the axis of the dipole is given by 1 by 4 pi epsilon 0 Q divided by x square plus d by 2 whole square to the power 3 by 2. This is the final answer for the electric field at point P. Now, let us look at a limiting case. That is, x is much greater than d. I'm sorry, there is a d here in the numerator. So if x is much greater than d, the denominator can be written as the denominator. So x square plus d by 2 whole square 3 by 2 can be approximated as x cube. Substituting, or rather taking this approximation in the above expression, we get E of P equal to 1 by 4 pi epsilon naught Q times D is equal to the dipole moment P. So therefore, P divided by x cube. Notice an interesting aspect of this equation. The electric field due to a dipole varies as 1 over r cube as compared to the electric field due to a point particle, which varies as 1 over r square. This completes the lecture on the principle of superposition of electric fields as applied to the electric dipole.